So a little bit of theory before we go to the other method is this thing called the intermediate value theorem. And this is like a specific thing that I am told that I have to teach you in this course. It is a learning outcome. And what it is that if you put different values in for x and you look at the resulting y values, if the y values go from positive to negative, then you know that there was a real zero between a and b. So what I mean by that is that if you took a graph that looks like this, and you took an x value a, and you took an x value b, and you looked at the resulting y value. So if I looked at the y value at this x value a, it would be negative. And if I looked at the y value for this x value b, it would be positive. Since the graph went from a negative y value to a positive y value, that means that you had to go through the x-axis, meaning there had to be a zero between those two x values. But if you plugged in a and b, so let me just give you a different graph. I'll just do it below. If you had a graph like this, where we know there's an x-intercept here, but if I picked in a value of a here, and I picked in a value of b here, when I looked at the resulting y values, they'd both be negative. So even though there was a zero between them, I couldn't determine it using the intermediate value theorem. So that is just like a one-off thing that you have to look at, and it's kind of a theory thing, right? Do you understand if the y value goes from negative to positive or positive to negative, that you had to go through the x-axis? And do you understand that if your x values go from negative to negative, that maybe there was an x-intercept, or maybe we picked an a and b value all over here and there wasn't one. So we couldn't use the intermediate value to determine if there was a real zero between there. So this is the first thing. This is the intermediate value theorem. So all we're going to do is literally plug in two values of x and look to see if the y values change or not. So let's try this one. We're going to plug in x is negative 4. We would get negative 4 cubed plus negative 4 squared minus 8 times negative 4, which would give me, oh, I do have a calculator, yes! So negative 4 cubed plus 16 plus 32. See, even when I grab a calculator, I don't fully use it. So I end up with negative 16 as my y value. So when x is negative 4, y is negative 16. If I plug in negative 1, I get negative 1 cubed plus negative 1 squared minus 8 times negative 1. That's going to give me negative 1 plus 1 plus 8, which is an 8. Interesting. So since the y value goes from a negative to a positive, did we go through the x-axis? Yes. There is, now here's the other catch, at least 1 0 between a and b. Because there was a sign change. If you didn't get a sign change, you would say the intermediate value cannot be used to determine if there is a real zero. Okay, but I find that this theorem kind of leads us into the other method of graphing. And again, like I said, none of you are going to use this method, but we are going to use this when it comes to rational functions. And I find that if we do it now, that theory might stick, so that when we do it with rational, you can kind of see how they're working. And like I said before too, you might use this to check your graphs. So what you're going to do is break up your x-axis into your critical values, which are your x-intercepts. So this polynomial function, which we've already graphed, has an x-intercept of 0, an x-intercept of 4, and an x-intercept of negative 3. Then we want to look at the intervals that this is breaking up. So there's an interval between negative infinity and negative 3. There'd be another interval between negative 3 and 0. There'd be another interval between 0 and 4. And lastly, there'd be an interval from 4 to infinity. And then what we're going to do is test an x value. So we're going to pick something in the interval. So here I'm going to pick negative 4. Here I'm going to pick negative 1. Here I'm going to pick 1, and here I'm going to pick 5. So these are my test values of x to determine the sign on y. So again, we're not graphing, so I don't care the actual value of y. I care the sign on y. So if we take this function and we plug in, first of all, negative 4. I would get negative 3 times negative 4 squared times negative 4 minus 4 cubed times negative 4 plus 3. And again, we're not finding the exact value of y because it won't fit on this grid, I can guarantee it. Instead, we just want to know the sign. So what I do is I cheat. So you can plug this into your calculator and get a value, but for me, I'm lazy. So I'm going to look, okay, that's going to be a negative, that's going to be a positive, that's going to be a negative cubed, which will be negative, and then this is going to be multiplied by a negative. So since I have 3 negative signs here, this is going to be a negative value for y. So I know that this graph is going to start somewhere down here. Actually, let's break up this x-axis too. So I know to the left of negative 3, my y values are going to be negative. Then let's test a value like negative 1. And we're going to do the same thing. So negative 3 times negative 1 squared, negative 1 minus 4 cubed, negative 1 plus 3. This is going to be a negative number times a positive number because it's squared, times a negative number because it's negative cubed, times positive this time. Okay, so my graph is going to go positive. So I know that between these two x-intercepts, my graph is going to be positive. Then we're going to look in the next interval. So we're going to pick 1. We've got negative 3 times 1 squared. Whoa, 1 squared times 1 minus 4 cubed times 1 plus 3. And so this is going to be a negative, positive, negative, positive. So this is going to be positive as well. So interesting. I'm going to stay positive, which means this must have been a touchy part. And then we're going to take an interval to the right of 4. So we're going to plug in 4. This is very time consuming. Learn multiplicities. Negative 3 times 4 squared times 4 minus 4. Oh, sorry, I'm not supposed to be testing 4. I got to test 5. Sorry about that. The x-intercept is 0. The interval is 5. So we're going to put a 5 in here. Then we're going to put 5 minus 4 all cubed. And then we're going to put 5 plus 3. So this is going to end up as a negative, positive, positive, because 5 minus 4 is 1 cubed, times a positive. Ooh, it's negative. Cool. So I'm going to keep going down. So what did this do? Well, it did the end behavior and the multiplicities for us. We know that this is a 1, 2, 3, 4, 5, 6. We knew that this was an even graph with a negative leading coefficient. So that's going to be from quadrants 3 to 4. That checks out. We know that this x-intercept had a multiplicity of 2, so it touched. We know this had a multiplicity of 4. It flattened, which you cannot see. So I think the downside of the interval system is you don't get the flattening, but whatever, we're not graphing anyway, so it doesn't matter. And I just give you credit for the fact that you had to do all of this work, which I wouldn't want to do. So you don't have to flatten. And then at this x-intercept of negative 3, the graph crossed. So again, this is another method of graphing or a way to just like check. Pick a point on your graph. Does it come out? So we're not looking at the exact value of y, but does it come out positive or negative? So if we compare this to the one we did when we were using multiplicities, this is the exact same equation. You'll notice it went through, touch, flatten, whereas ours went through, touch, through. Awesome. So that is your other method of sketching, but really the only stuff that you're going to be tested on for this is just that intermediate value theorem.